Hello everyone and welcome to this exciting journey into the world of calculus. This course is designed to guide you step by step through the fundamental concepts of calculus, building your knowledge from the ground up. Throughout this course, we will explore everything from the very basics, like understanding functions, limits, and derivatives, to more advanced topics like integrals, infinite series, and differential equations. Each lesson is designed to be easy to follow with clear explanations, practical examples, and interactive problems to help you master the material. My name is Shaunak and you're watching this video on my channel, Physics for Students. Welcome to the first lesson in understanding calculus, understanding functions. Well, first we come, what is the basic fundamental where we start with calculus is a function. Now, you can imagine that function, for example, f of x is a function. These are a tool for describing the real world in mathematical terms. However, a function can be represented by number one, an equation. It can also be represented as a graph. Also, it can be represented as a numerical table or any kind of a verbal description. And we will use all these four representation in order to make things much more clear. Now, for example, if I go by what is representing the function by an equation, it looks something like this. Now, this is a quadratic function representing an equation. If I follow by a graph, now this is a kind of a parabola which is going upwards. So it shows that this function can also be represented as a graph. If I talk of a numerical table, for example, f of x equals to 2x plus 3 or something like that, where the values of 0, 3, etc. are taken on. So you can even, represent as a numerical table. Or you can say something like this, f of x equal to 2x plus 3. And you can say this function takes a number, multiplies by 2 and then adds 3. So it is a kind of a verbal representation. So equation is there, graph is there, numerical table is there, and verbal description is also there. Now, how does it relate to calculus? This is a very important part because we know functions, we have dealt with functions, and we will deal with functions in this series of course. But how does it relate to calculus? Let us look into that. Now, as you see, calculus is often used to model real world phenomena. It is not something which is right on paper for researchers. For example, if you want to calculate something which is going very fast, a motion. If you want to calculate growth, maybe a population or anything else, or you want to calculate a decay of any particular thing, then calculus is very much used. So understanding the function allows you basically to translate these real world scenarios into kind of a mathematical language. So whatever is happening out in the world, in order to translate it into mathematical language is calculus. And this is essential. Why? Because for solving problems in calculus, it's very simple. Now, since calculus deals with concepts like limits, derivatives, integrals, which are based on functions, that is why we have to have a very good solid grasp of functions, and it is essential before we go into much more advanced topics. So yes, I can say that overall a very good understanding of function is essential. And let me tell you, most of the students that I have seen in schools and colleges or upper grads also, they do not understand the importance of understanding a function. They do not understand how deep a function can go and to understand those, details. And then when you face problems in calculus, you see that this is not my cup of tea, I cannot do calculus, it's difficult, etc. No, because the basic root of function is not clear. So overall, I can tell you that we aim to ensure that you have a versatile understanding of functions, which is crucial in order to master calculus. Now, when we talk of function, the first thing that rings our mind or rings our bell is what is called a domain and a range. Now, these are technical words, but I will make you understand very easily. Now, say for example, this is water, right? It is boiling. So the temperature at which water boils depends on what? It depends on what is called the elevation above the sea level. That means the boiling point drops as you move up or as you ascend. For example, the interest paid on cash investment, what does it depend on? It depends on the length of time the investment is held, or you are giving an EMI or whatsoever. Even the area of a circle depends on the radius of the circle, isn't it? So the question is that the distance of an object travels at a constant speed along a straight line, and it depends on what? It depends on the elapsed time. Now, in each of these cases, the water boiling, the investment, the radius of the circle, the distance a body travels, in each cases there is one variable. For example, we say y, which depends on another variable. We call it x, and we write it as this. It depends on another variable, right? We might call x. We say that y is a function of x, and we write is symbolically something else as this, and we tell y equals f of x. So this is nothing. This is not any mathematical language. It is just telling that if the water boils, it depends on another variable which is above the sea level, and that is x. If you invest certain amount of money, it depends on the length of time of the investment, that is y equals to function of x. So what happens in this kind of a notation, y equals to f of x? The symbol f actually represents the function. The letter x is the independent variable, and it representing the value of f, and y is basically the dependent variable or output value of f at x. So that's it. That's it. Very simple. That is why it is called y equals f of x. Otherwise, we have to depend that the boiling of water depends on the elevation of sea level, and as it changes. So we mathematicians, we try to avoid those big literary languages, and we try to write it in a comprehensive short manner. So we write y equals f of x. Now I would like to now show you a very mathematical definition of a function. And the mathematical definition of a function says that a function f, don't worry, I will be explaining this step by step, f from set D to set Y is a kind of a rule that assigns a unique single element, for example f of x in Y, to each element x in D. Now first of all, I would like to give you a very clear understanding of this definition, then we will make those definitions step by step and put it across. So I would like you to imagine a kind of a machine that you put something into it and it gives back something back. This is a simple way to think function. So let us example this one. There's an input, you're putting maybe flowers and sugar, and it is giving what? Beautiful bread. So there's an input and there's an output. So input is the thing you put into the machine, and output is what the machine gives you back. So for example, this is something you're putting into the machine, this is what it gives you back. So for example, if you put in 2, it will into a function, it might always give you 4. So if you put 2 in again, it will still give you 4. So in mathematical terms, what we see is that a function is a rule. That means what is the rule that you're setting in the machine? That is a rule that assigns a unique output to every output. For example, you're putting some cookies and sugar, it would give output to a cake. So what it would give output, that is the function. That is the rule that you're assigning. And input is represented by x and output is represented by f of x. And that is what this definition has told. Now what we will do is that we will break down this definition step by step and make you understand in a pictorial manner coming up into the next part of the video. So, and set, I'm so sorry, set is just a collection of objects. We will look into it right now. So we will keep this definition as it is, and now I would first take this part, a function f from a set D to set Y. How does it mean? This means that we have a function named f. This takes input values from a set that is a collection of objects called D, and f actually produce output values that belongs to another set which is called a Y. So let me repeat it. We have a function f, it takes input values from a set called D, and f produces output values that belong to a set called Y. Now we will go to the next part. What does the next part tells? It is a rule that assigns a unique single element f of x in y to each element x in d. How does it look like? This means that for every input value x in the set d, this means that every input value x in the set d, the function f will produce exactly one output. It will produce exactly one output, that is f of x, and the output value of f of x must belong to the set d. Set y. Yeah. So let me again show you one by one. I will again take that. This is very important. That is why I am repeating. It is a rule that assigns a unique single element f of x in y to each element x in d. This means that for every input value x in the set d, the function f will produce exactly one value, that is f of x, and the output value of f of x must belong to the set y. As simple as that. Now, taking this forward, I would like to show you another step clearer picture, which is this one. Now here what you can see, that each arrow associates an element of the domain D with a unique or single element in the set Y. So the arrow indicates that f of a or whatever is associated. For example, this one. So here we can see that with f of x is associated with x here. The x is associated with f of x. And arrow indicates that. And this one, a, f of a is associated with a. So it goes in this way. This part and this part. So from here this becomes very clear. So f of a is associated with a and f of x is associated with x and so on. And here is something you need to have a note, that this part, that a function can have the same value of two different input elements. A function can have the same value in two different input elements in the domain, as you can see, f of a in this figure, but each element x is assigned to a single output value f of x. Each element of x is assigned to a single output value f of x. But it is also noticed that the function can have the same value at two different input elements in the domain as occurs with f of a. In case of f of a, it is both the two, but each element of x is a single output value of f of x. It's one output value, and a gives as in f of a, it actually gives two values. So it can have the same value of two different elements. F of a has got two different elements, but each element of x has got a single. This is pretty important. Now from here you must note that function can also be given by a formula. So, and this is very common in calculus. Often a function is given by a formula, and it actually describes how to calculate the output value from the input variable. For example, if I take this one, a equals to pi r squared, it is a rule that calculates the area of a circle, and this area of the circle with a radius r. As simple as that. So it calculates the radius r. So when we define a function y equals to f of x with a formula and the domain is not stated, remember, we are defining a function y equals to f of x with a formula, for example pi r squared, and the domain is not stated explicitly or restricted by context. It is basically, yes, one. The domain is not stated by the domain and it is not explicitly written, then this is called a natural domain. So I again repeat, these are very fundamentals. When we define a function, if the formula and the domain is not stated explicitly or restricted by context, the domain is assumed to be a very large set of real x values or real numbers, for which the formula gives real y values. So we assume that there is a real x value which gives rise to real y values, and it is called a natural domain. When it is not stated, that means the domain is quite large. Now if we want to restrict the domain, for example, we must say so. How we do that? The domain of y equals to x squared is the entire set of real numbers. To restrict the domain of the function, we set the positive values of x. We could write y equal to x squared where x is greater than 0. So one part is natural domain. We don't have a artificial domain over here, but in order to mention that those entire set of real numbers we want to restrict, we do that. And as you can see, y equal to x square, we can change the domain to which we apply. And this is y equal to x square 0, infinity. And the range of y equal to x squared will be x is greater than equal to 2. And this is actually the set of all numbers obtained by squaring numbers greater than equal to 2. We will look into this later. But right at this point of the video, what we can understand is that if the domain is not mentioned, it is very wide and it assumes real number which gives output of real x value, which gives output to real y values. It is called natural domain. If we want to restrict this, then we can mention this one, y equal to x square, where x is greater than 0. And we can even change the domain from 0, infinity, and the range of y equal to x square, where x is greater than equal to 2, is a set of all numbers which are obtained by squaring numbers which are greater than or equal to 2. Now, the next thing which becomes important is that when the range of a function is a set of real numbers, the function is said to be real valued. So when the range of a function is a set of real numbers, the function is said to be real valued. And the domain and ranges of most real valued functions are obviously real variable, and we consider the intervals. Now, so that brings us to this part, is that let us imagine again a function f is like a machine that produces an output value f of x. And in its range, whenever we feed an input value x from its domain. And we have seen what domain is. So you can imagine the function keys on a calculator. For example, this is a calculator and you've got a function key which is a kind of a function of a machine. And this function key, for example, gives rise to the square root of x. And this square root of x on a calculator gives an output value, the square root. Whenever you enter a non-negative number x and press the square root of x key, it would give rise to this. So it's just an analogy that function keys on a calculator gives an example of what is a function. So you press this and you get this. So there's an input and there is an output. The question is that now, for example, if we take a function, domain and a range, and the examples are this one, y equal to x squared and this, and we take y equals to 1 upon x and this, I have a question that can we verify the domain associated with the ranges? We need to verify, otherwise we cannot. How can we say that? In order to do that, I will just show you with very simple examples what do I mean by that. Now, if I take the formula y equals to x squared, which gives a real y value for any real number x. So the domain minus infinity to plus infinity, I would say the range of y equal to x squared equal to 0. Because the square of any, this one, y equal to x squared 0, this part, because the square of any real number is non-negative and every non-negative y is the square root of its own square, which is y equals to square root of y squared for y is greater than equal to 0. So what do I mean by this? I am trying to give you an idea that this gives a real value number. So the domain is minus infinity to plus infinity. The range of y equals to x squared from 0 to infinity, because the square of any real number is non-negative, obviously. And every non-negative number y is the square root of its own, which is this one. And if I try to take an example, so this proves that the domain is so. Now, for example, the next example, formula y equals to 1 upon x, it gives a real value for every x except x equal to 0. Now, when I say it gives a real y value for every x except x equals 0, what do I mean? So, for example, if I take a value of x equals to 2, then y would give 0.5. If I take x equals to minus 3, it would give minus 0.33. But what would happen if I take x equals to 0? So this expression 1 upon 0 is undefined in mathematics because division by 0 is not allowed. As a result, there is no real value of y when x equals to 0. There is no real value of y when x equals to 0. And the function I have not shown is a vertical asymptote at x equals to 0, meaning that the function blows up or goes to infinity, which mathematicians do not like. So there is no real value. So from here what I can summarize is this. The formula gives a real value for y for every real x except x equals to 0, because here the function becomes undefined. Now let us take another example and let us see what we can do. We take the same function domain and range where y equals to square root of x. So y equal to square root of x again gives a real y only if x greater than or equal to 0, and the range of y square root of x is 0 comma infinity. And this one, every non-negative number is squared. Now here you see, if I take x equals to 1 and y equals to square root of 1, what happens? Now you can understand from here that this is not a real number. This is an imaginary number. So from here what we get is that this means that you can only take the square root of non-negative numbers. If you try to take the square root of a negative number, you will get an imaginary number which is not a real number. So again it proves that y equals square root of x, this is the domain and this is the range. From here, as we have shown those in terms of numerical functions, algebra formulas, etc., we also need to see what is the graphs, that how we can represent functions in terms of graphs. So the graph of the function y, for example, f of x equals to x plus 2. So if I take the set of points with coordinates x and y, for which y equals to x plus 2, its graphs look something like this. Simple, straight line. So the graph of a function f here is useful. Why? Because if f x comma y is a point on the graph and y equal to f of x is the height of the graph, that means a point above or below the point x, the graph would look something like this. And here you can see the height may be positive or negative. I've shown this part depending on the sign. So if x comma y lies on the graph of f, then the value y equals to f of x is the height of the graph above the point or below x, where f of x is negative. So this is how it actually looks like. Now if I take this example, if I want to graph the function y equal to x squared with this interval, so what we can do first is that we need to make I mean to say very sketchy kind of a diagram. I want to make a table of x and y's pairs where y equal to x squared, that is the condition given. So it would look something like this. And from here I would plot the point whose coordinates appear in the table and draw a smooth curve, and which would somehow look like this. But here is a big question. The question is that how do we know that the graph y equal to x squared does not look like any one of these curves? It might look like this, the left hand side, I mean to say the second from the left hand side and the extreme right hand side. So how we can do that? And now in order to do that we could plot more points, but how do we connect them? So what happens is that the basic question that remains over here is that how do we know for sure that the graph looks like between the plots on a point? How do we connect them? So this answer will be given by calculus, as we will see. So calculus can only provide the answer. In the meantime, let us settle for plotting points and connecting the best as we can, and we get this kind of a graph. We come to the next part where we are representing a function numerically. I told you we got a graph, we got equation, we have got verbal, and we have got a numerical way. Now, when we talk of numerically, this particular part, we have seen that how a function may be represented by an algebraically, by a formula. But how do we represent a function numerically? Now, numerical represent of a function is required by engineers and experimental scientists. So we do a kind of a scatter plot. We can do that. Now, for example, when a musical instrument, I would say, produces a sound, it causes the air molecules to vibrate. For example, this guitar. You pluck it and the string vibrates, pushing and pulling the surrounding air molecules. Now these vibrations, areas of high pressure and low pressure, I would say compression and rarefactions, which travel outward from the source of a wave, this is known as pressure wave. So when you pluck it, the string vibrates, pushing and pulling. Now the frequency and of these pressure waves, that means how many compressions and how many rarefactions occur per second, determines what is called the pitch of the musical note. Higher frequencies produce higher pitch notes, Lower frequencies produce a lower pitch notes, and the unit of frequency is hertz, which measures the number of waves per second. Now, if I try to take a kind of a rough estimate of this kind of a time and pressure kind of a table, then I can plot an XY graph where I'm measuring pressure in the X direction and time in the Y direction, and then I can get a graph. I plot those points roughly on the X and Y axis, and then I get a graph like this. And then I try approximately, remember I have not actually plotted this on pen and paper, just graphically on computer. I can say that this is a smooth curve through the plotted points, which gives the graph of the pressure function, which is represented by the left hand side table data. So this is also representing a function numerically and then plotting it. Now there is a very important, a kind of a notion, or kind of a criteria. Yeah, that's a nice word. A criteria of a vertical line test. That means a function cannot always be a function. So here I would like to tell you is what is called the vertical line test for a function. So not every function, not every curve in the coordinate can be graph of a function. For example, a function f can only have one value f of x for each x in its domain, so that no vertical line can intersect the graph of a function. Let me put it in to each input x, for every x there must be only one corresponding y which is relating to f of x. I will try to put it in a nice easy language. Here it is. A vertical line cannot intersect the graph of a function more than once. This is because if a vertical line crosses the graph at more than one point, it would imply that the function gives more than one output, and how that can happen for the same x, which violates definitely the definition of a function. So if you're getting a function and if you plot it and if you see something odd happening like this, then that means it is a test, it has failed, it is not a function. Let me show you some quick examples. For example, this part, this is a vertical line intersect the graph only once, right? So that's fine. The blue and the red ones and the green are not over here. And also, if you can see over this, it has been intersected twice. That means it is not a function. A few more examples which will help you. A kind of a curve like this, it has intersected twice, so this is not done. I will also like to show you this kind of an example. For example, the circle is not the graph. This is not the graph of a function because it fails the vertical line test. So the red dots denotes that it has got two intersections. This one, so it is cross. So it has got two intersections. Now this one, the upper semicircle, is the graph of function y equals to square root of 1 minus x squared. This is okay because it has intersected only once. And the lower semicircle, if you see, it is also okay because it has intersected only once. And that is why it is minus square root of 1 minus x squared, because it will come below the axis. So if you see a function and you plot it, then you pass the function. It is called a vertical line test function, very central to our understanding of calculus, and this is how it does. So we will now take a pause on today's video because this is just starting with the function, and we will continue further with the function before going into differential equations. And I would like to thank you very much for taking up time to watching this video. If you have liked the video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can also contact me at this email ID, and you can subscribe to my other channel related to general theory of relativity. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back, and this will continue the calculus and the other courses that I have started, and we will see you soon in the next video. Till then, may the good Lord be with you.